In this video, we're going to be exploring this concept of effective population size and use the equations that Jed mentioned in his video. And we've tried to set up a spreadsheet that will let us explore the various ways in which we calculate effective population size and try to get at the underpinnings of why things are actually happening and why they're calculated as they are. The spreadsheet template is set up with relatively few inputs, which are shaded green. You can enter the number of males down column B and the number of females down column F. So for example, if we have a population that begins with 5 males and 10 females, we'd enter those numbers for generation 1. And then we can also specify what the number of males and females will be like in the next generation. So let's enter some numbers there. 50, 10, 50, 10, and 50. And we'll copy the males, and we'll copy them right into the female. So for this example, there is a little bit of deviation between the males and females in the first generation, but thereafter the male and female sex ratio will be the same. Now the reason this is set up like this is so that we can really play with changing the population trajectory. We can send our population through a bottleneck. We can keep the population size very small for multiple years or send it through a bottleneck for a brief period of time and then have it come out of the bottleneck. And along the way, we're going to be tracking not only the numbers of individuals, but we're also going to be tracking the genotype frequencies and the allele frequencies, and that will help us to explore how these effects may actually change the evolutionary trajectory. So effective population size is really driven by a couple of things, and that is, one is genetic drift, which we covered in a separate video, and the second is non-random mating, which we've covered also in another video. But this concept lets us wrap those things together and explore what it means to have a population on a landscape that has a different effective population size. And Jed gave us some examples, and the examples were something like this. You may go out and observe 100 individuals on the landscape and count them in your census. But that population of 100 individuals may actually behave like a population of 20 individuals from a genetic perspective. And that 20 individual population is called an ideal population. That's a population that has no natural selection, no gene flow, no mutation, the mating is totally random. However, it does experience some genetic drift because all populations experience some level of genetic drift. So our population of size 100 is acting more like a real population, an ideal population that is only the size of 20. And of course you can see why this is of such interest from a conservation perspective. Now Jed talked about calculating the effective population through 3 different methods. They're highlighted in these red boxes. One is through calculating the harmonic mean, one through the sex ratio, and the third through the variance in reproduction. And we'll go through all of those in this exercise. So this might be a little bit of a longer exercise, might be a good time to go grab that cup of coffee. To begin, we've got now numbers of males and females, and we can calculate the total population size down column L. And that will simply be the number of males plus the number of females, and we'll copy this through. And over on the side of my spreadsheet, I've got a graphic that is kind of pre-populated. And what you see here is the generation number on the bottom axis and the population size on the y-axis. And so by definition, we have established a very fluctuating population that goes up and down between 15 and 20 individuals and 100 individuals. So that is shaded blue, and that represents our census population size. Now at this point, we're ready to calculate two estimates of effective population size. Let's start with the harmonic mean estimate. Jed went through this in his video, so we'll move through this fairly quickly. The numerator is the number of generations under consideration, and the denominator consists of the reciprocal of the population size. So we'll start by entering the reciprocal down column O, and that's going to be 1 over the population size. And when we carry this through, what you can see right away is that when the population size is small, the reciprocal is larger, and as the population size gets larger, the reciprocal gets smaller. And that's what Jed meant when he said that these smaller population sizes carry more weight in the calculation. So that represents these terms in the denominator. So now in column P, we can calculate the effective population size as the generation number, that's T, divided by the sum of the reciprocals. And for year 1, we're interested only in the year 1 reciprocal, but instead of typing that in, we'll type in sum 05 through 05 and anchor the reference to the first 05. In doing so, we can now pull this equation through, and we'll be calculating the harmonic mean, the effective population size, as a running total. So in year 1 we have a measurement, in year 2 we have a measurement, and in year 3 we may have a measurement, and so on. In year 3, we're considering 3 generations, and the denominator consists of the 3 terms from year 3, 2, and 1. And you can see that we've plotted this as well, and this is plotted in red. This is the effective population size based on the harmonic mean. Now, what do you notice right away? Wow, what a difference. The census population size can grow and shrink and can be quite large, but the effective population size is really quite low no matter where we are. And why might that be? Well, we started off in year 1 with a population size of 15 animals or plants, and the harmonic mean was also 15. That should make sense, right? Because the generation is 1, and 1 divided by 1 over n1 is simply going to be n1. But in year 2, generation number 2, this population rose to 100 individuals, but you'll see that the effective size is kind of slumbering along. It doesn't rise that much to 26 individuals. And why would that be? Well, conceptually, the reason is that all of these individuals arose from a very small parental population. And as a result, these individuals have a high inbreeding coefficient, like we calculated in our inbreeding exercise. So that is what's driving these effective numbers to be so low. And they don't recover very well because the population is continuing to go back and forth through these high and low periods. Now, what would happen if our population size was big at the beginning? Let's make this population of females grow to 150. Well, now we have quite a different scenario here. In year 1, our population size on the ground was 155, as is the effective size. In year 2, the population dips to 100 individuals, but here you can see that the effective size is actually larger than the census size. Now, why would that be? Well, it's the reverse of what we just experienced. We have a smaller number of individuals that could potentially be coming from a very large parental population size, and so the genetics of these individuals will be more and more diverse. Let's set this female population size back to 10. And now we can look at this from the perspective of the sex ratio. And the equation for the sex ratio is 4 times the number of females times the number of males divided by the total population size. And we'll enter that directly. 4 times the number of males stored in cell B5 times the number of females, and we'll divide that by the total population size. And here now we have another view of what the effective population size is. And let's pull this through and graph it as well. And what you can see here is that our effective population size as calculated from the sex ratio almost perfectly matches the census population size. The only exception is this very first year when our number of males and females differed slightly. Here, with a little bit of difference between the mating males and females, we end up with 13 individuals as the effective estimate. But other than that, our population size on the ground perfectly matches the effective calculations because for every male there is one female. Now in this model, it's important for me to note that these are all breeding individuals, and that after they breed, these individuals will pass away. So there are no overlapping generations or non-overlapping generations in this particular model. We'll be able to now change these sex ratios as well as change this fluctuating population size and explore these consequences in more detail. So the next version of this equation is this variance in reproduction. And to get to that point, we need to actually simulate reproduction. And that's what we're going to be doing in this portion of the spreadsheet. We'll enter our males down column B. We'll indicate whether they are present in the population or not. We'll give them a genotype. We'll do the same thing for the females. Then we'll choose a random mom and a random dad. We'll simulate the process of meiosis, and we'll form offspring. And then we will assign sexes to the offspring, and along the way we'll be able to count and identify how many offspring each individual, each parent has produced, and in doing so we'll be able to calculate the effective population size using the variance in reproduction method. Now before we do that, let's first establish the genotypes for our 5 males and our 10 females. And these are shaded green so that you enter the number of A1A1 homozygotes and A1A2 heterozygotes, and we'll enter an equation in cell E5 to help us not have to enter that and just calculate it by default. So here let's assume that there are 2 A1A1 individuals, 1 heterozygote, and then the number of A2A2 homozygotes is going to be the total minus the homozygotes A1A1 and minus the heterozygotes. For these 10 females, we need to account for 10 of them. So let's say that there are 4 A1A1, 2 heterozygotes, and again we'll calculate the A2A2 homozygotes by subtracting off the other kinds of homozygotes and the heterozygotes. Now you'll know you've made a mistake if these entries are negative, so pay close attention because really these are the only inputs that you make into this model. The rest of the spreadsheet is pretty much calculated for you. In order for us to identify our individuals, we need to summarize where we are and what is our status of our population, and we'll do that in this grid. And the way the spreadsheet is set up is that you can enter the number of the generation you're concerned with. So this represents the parent generation. So if we start with generation number 1, what we want is a formula that will return the number of females the number of males, and the number of each type of genotype for each sex. And we'll be using a function called the index function, and this is a really handy function if you haven't used it before. This function has 3 arguments, but only 2 are required, and we'll only need 2 for this entire exercise. And we'll use this repeatedly, so pay attention. The first argument is an array, and that's simply a group of cells you want the spreadsheet to inspect. I'm interested in counting the number of males in generation number 1. So my array will be the array of male abundances from cells B5 to B10. And the row number is simply, well, what number do I want to return? And I want to return the value that's stored in cell D2. We'll go ahead and anchor that reference to cell D2. For the males, we can also fix the references to the array itself. So if I indicated that we're interested in generation 2's number, then it's going to go to this array and it would return the second element, first, second. We can leave the third argument blank. So that correctly is returning the number 5. And now we can pull this over and simply drag the reference from the males over to the females, and that should give us the correct number of females. And let's double check our work. If we enter the number 2, we should see that we're now considering in year 2 50 males and 50 females. And we'll be using this ability here to enter a new number when we are doing macros with this spreadsheet in the sandbox. Now let's use the same functions to identify the number of A1A1 homozygotes, heterozygotes, and A2A2 homozygotes for males and females. So let's do the index function once more, and later we'll just simply be typing this function because you'll know the syntax. So the array for the males is going to be cells C5 through C10, and we'll anchor that reference, and the row number will be once again D2.